Okay, good morning, future presidents. You guys don't even respond anymore. Good morning, future presidents. Thank you. Okay, today we are talking about a new subject, electricity. Okay? So let's get started. Electricity. So, electricity is the transfer of power or information by electrical forces. Okay, so electricity is the transfer of power information, and then we've introduced another new concept here, which is electrical force. Okay. This is a new type of force that we are going to be studying. Okay. And we can call it the electrical force, or more properly, we call it the electrostatic force. Static here just refers to the fact that the electrical charges that we're talking about are presumed to be at rest, or primarily at rest. Okay. So the electrostatic force is a new fundamental force. Well, not so new, new to us, a new fundamental force of nature. Okay, and that is just like gravity. Gravity is also a fundamental force, the other fundamental force that we have studied. Okay, so electrostatic force is a new fundamental force, similar to gravity, but some very important differences between the two. Okay, so electricity. Electricity plays a very key role in modern society. In fact, you could argue that electricity plays the defining role of modern society. Okay. So let's just list some of the applications. So the first one that usually pops to mind is the transfer of power. Okay, so the sockets in your wall are, of course, electricity. We can store energy. So we're talking about batteries or similar devices that can store electrical energy that we can turn to work. We use it to run appliances. These are certainly key to modern society. Okay. We use it for light and occasionally heat. Okay. That's for lighting our houses, our homes, and heating our homes. Okay. We use it for transportation. For example, BART runs on electricity, and we're seeing more and more cars that will be running on electricity as we go forward. Okay. And then, of course, there's computers, telecommunications, entertainment. Okay, this list can go on and on. So a lot of the key defining features of modern society, of course, rely on electricity, both for power and for the transmission of information. Okay, so let's start by looking at the electrostatic force from the very fundamental nature, or from the most fundamental level. So this force arises from electrical charges. Okay, which we are going to be discussing in more and more detail today. So let's look at our introduction to electrical charges from the most basic level, from atomic structure itself. So let's look at atoms and what they're composed of. So they're the smallest piece we can have, the smallest chunk of regular matter, and I think most of you are familiar with this picture we have of the atom, that it is composed of neutrons and protons, okay, that form inside of a nucleus. Okay. And then orbiting around that nucleus are electrons. That's a really bad picture of an atom. I can't let that one stay up there. Okay, so here's our electron. Okay, I drew it really big, but we should be thinking about it really small. Okay, there we go. Electron. Okay, there's our electron, and it's orbiting around this nucleus. Okay. There we go. That's a little bit better. Okay, my kindergarten teacher, be proud. So there's an atom. So let's put some names on these. So this is the nucleus. Okay. And it's composed of very tightly bound neutrons and protons. Neutrons and protons are very similar. They have almost identical masses. They are both relatively massive particles. They have a lot of properties in common, except for neutrons do not have any electrical charge, and protons are electrically charged. Okay? So, but these are bound together in the nucleus, okay? And then they are surrounded by electrons. Which orbit the nucleus. Okay? The classical picture of an atom would have these orbiting the nucleus just like planets orbit the sun in the solar system. Okay? So when we get to quantum mechanics, we're going to see that picture is quite dramatically altered. Okay? But still the same basic idea is that the electrons are surrounding the nucleus, orbiting the nucleus, okay, at a distance from it. Okay, let's put some characteristic size scales on this. I've drawn it completely out of proportion, okay, because it would be very difficult to draw this in the right proportions. Okay, so a typical nucleus is on the order of, in size of 1 femtometer, which is 10 to the minus 15 10 to the minus 15th of a meter, so very, very tiny. Okay. Whereas the electrons orbit at a size which defines the atom. So the atom is defined, the size of it is defined by how far out these electrons are orbiting around. So the atoms itself are on the order of what we call 1 angstrom, which is 10 to the minus 10 meters. Okay. So we're talking about extremely small size scales, but let's put a little perspective on this. Think about how different these size scales are. This is 100,000 times bigger than the size of the nucleus itself. Okay. So let's see, if the nucleus, if we thought of the nucleus as the size of a basketball, so just to get a little bit more human perspective, if the nucleus were the size of a basketball, the electrons would be orbiting a distance of about 20 miles. So that gives you the size scale of the electrons to the nucleus in an atom. And the electrons themselves are very tiny, so they'd be about the size, I guess, of a grape orbiting at 20 miles from the nucleus. Okay? So atoms are very largely empty space, okay, which make up the bulk of the world around us. So a lot of empty space in atoms. Okay? Let's see, these components. So we've got the proton, the neutron, and the electron. You can find their exact masses and charges with units in the book, but I just want to do a comparison between them so we can see, how they react relative to each other. Okay, so there's the proton, the neutron, and then the electron, which is orbiting that nucleus. Okay? So the mass for these, like I said, you can find it in the book with units, but the proton, if we just say the proton has a mass of 1, just for comparison, we just want to see how these compare with the proton in mass, then the neutron is actually almost identical. It's not exactly 1, but it has almost the same mass as the proton. Okay? And for comparison, the electron has a mass that is 1/2000th of the mass of the proton. So the electron is very light by comparison, 2,000 times less massive. Okay? So that's going to be really important when we start talking about currents in a few minutes, to remember that the electron is much, much lighter than the proton. Okay? And the neutron is not charged, so we won't be talking about it much more at this point. Okay, so the electric charge, protons, let's just assign them a charge of +1. That is the charge of a proton. Every single proton has the exact same charge. We've never seen a proton that does not have a charge of +1. Okay. Neutrons are neutral, 0. They have no electrical charge. Okay. And then electrons have a charge of -1. Electrons have the exact opposite charge of a proton. Every electron has the same charge. We've never seen one that didn't. Okay. And it is exactly equal in magnitude and opposite in sign to protons. Let me write down a few points about these. Okay, and then we'll start doing some demos. So okay, so here's some points I want you to remember about electric charges. Ooh, this is bad, isn't it? I'm not going to use this board. There's too much stuff here. Let me go back over here. Okay, so here are my points that I want you guys to remember. First off, is that electric charges come in 2 types. Okay, and those 2 types are called positive and negative. Okay. We only call them positive and negative because Benjamin Franklin, who was the first great American scientist, called them positive and negative. Okay. We could have called them blue and peanut butter or anything we wanted to call them. Okay? So we just use positive and negative because that's our convention. There's 2 of them. We'll see when we have the forces that this makes assigning the direction of the forces kind of easy. But there's nothing inherently physical about us calling them positive or negative. There's just 2 different types of charges. Okay? There's the charge that we assign to a proton, which we call positive, and the charge we call the electron, which we call negative. Okay. So there are two types of charges. Protons and electrons have exactly equal and opposite charges. So the charge on the proton is exactly the same size as the charge on the electron. It's just of this different flavor. This is what we call positive and what we call negative. Fundamentally, is there a really good reason for this? Absolutely not. We don't understand that. We just see it. This is the way nature is. Protons and electrons have exactly the same charge. They're equal and opposite. This is the way that nature made it. So there's not a very good fundamental understanding of why the charge of the electron and the proton are exactly equal and opposite. Okay. There are plenty of theories out there, but I don't think that anything is definitive at this point. Some things in nature are just that way. And this is one of them. The charges are equal and opposite. So let's see, other points. Okay, so next point. There's a fundamental unit of charge. Okay, and in this unit, the protons we've already seen have a charge of +1, and the electrons have a charge of -1. Okay. We thought for a long time that you basically could not subdivide a charge as any smaller than this. Right? We eventually learned that there are quarks that make up protons, which actually do have charges of 1/3 or 2/3. We will talk about them later, but they are you can never get them alone, so it doesn't really matter for our discussions today. So whenever we're talking about electric charge, a charge, we can get very large charges, okay, on objects, but those large charges are always made up of individual protons and electrons, so it's always some multiple of this fundamental charge, okay, that shows up on the protons or the electrons. Okay, and then the last point I want to make before we get to something that is a little bit more fundamental is that electrons move much easier than protons. Okay, so electrons are 2,000 times less massive. So that means they are much easier to accelerate and move around than protons. Okay? So we're going to start talking about currents, which is just charge that is moving, so the flow of electrical charge. And also we're going to start seeing objects that are charged, so they have a net positive or net negative charge. But in most cases, not absolutely all cases, but in most cases when something is charged, it's because it's either gotten electrons that have been added to it or electrons that have moved away from it. And we only have a few situations where it would actually be protons that are moving, okay? So, because they're so much heavier, so much harder to move, the electrons move so much easier that usually when we have objects that are charged, it's because electrons have either been transferred to it or taken away from it. Okay? And when we're talking about like electrical currents in the walls, okay, we're talking about the flow of electrons because they move so easily. Okay, so there is a very basic principle which most physicists believe is true. It's one of these things that is almost impossible to completely prove, which is the idea of the conservation of charge. Okay, so we have a basic principle that charge as a whole is conserved, okay, and that the universe, we believe, has no net charge. Okay, I can't prove that to you, okay, but we have quite a bit of evidence for it just because the electrical forces are so strong, which we'll see in a minute, that that this is sort of generally believed, but I would say this is not definitively proved. Okay? So, but there is a second part of this, conservation of charge, whether we can create charge or not. And we believe the answer is no, that we cannot create a net charge. Okay, by that I mean, can we actually set up a physical situation where we just produce a positive charge? Okay? And we don't believe so. So whenever we produce a positive charge, we have to produce an equal and opposite negative charge. Okay? We can't produce one without producing the other. Okay? Likewise, we can have charged objects. Okay? We can charge up an object so it has a net positive charge, but that's expense of making a net negative charge on something else. Okay? There are fundamental reasons to believe that we can't create a positive charge without creating a negative charge at the same time. And we can separate them. We just can't produce a positive charge without having the equal negative charge or vice versa. Okay, so, okay. So we can't create the charges, but we can separate them. And then when we separate them, we will get positive and negative charges. So, for example, easy examples of creating electrical charges. I've got saran wrap, plastic wrap. Okay, turns out plastic wrap is a good way to charge up. These are just styrofoam balls. Okay, so I'm just going to rub this on here. And this is kind of like walking across a carpet. This actually produces the opposite charge of that. Plastic wrap likes to, you can see it's already attracted to the table there. Need to balance this a little bit. Saran wrap likes to take electrons. So when I rub it on here, it's actually pulling electrons off of the styrofoam ball and giving it a net positive charge. So the styrofoam has absorbed electrons to produce a negative charge. You can see that it's absolutely charged from this ball. It's already attracting it up. And I can start putting it over there, and you'll see it's moving this. This is not very well balanced. There we go. That'll help. Okay, you can see I've produced a net force on this just with the saran wrap and the styrofoam ball. So fun physics you can do at home. Okay, so let's see. This is fur, which I hope not a lot of you have at home, unless you have a cat or a dog. And here's the styrofoam ball. Fur does the opposite. It will give electrons, so it loses them pretty easily. So I can rub this on here, and let's see. Should I charge up before? Yeah, I charged up that one. If I rub that on here, I'm going to be producing the opposite charge on there. Okay, so that one's going to have a negative charge now. I think you can use felt for that, by the way. So let's see. I actually think the plastic wrap was working better. There we go. At least you can see I'm giving a little bit of a force there. If I pull that over here. Ooh. I used to do this when I was a kid, walking across carpets and stuff, and I thought I had superpowers. I was totally convinced. Alas, wish it were so. Okay, so we'll come back to that in 1 second. So, pretty easy to produce regions that have net positive charge and net negative charge. Okay, these are electrostatic charges, so static just means that they are stationary, they're not flowing. Okay? And there's obviously forces that are being produced through that. So, let's do a little, let me write it down here first, and then we will show that this is true. The reason that we have two different flavors of charges, and we have named them positive and negative, even though, like I said, that's just a convention. We could have called them whatever we wanted, is because electrostatic force differs very fundamentally from gravity in that it can be both attractive, like gravity, and it can be a repulsive force. It can push things apart. So, the electrostatic force is both attractive, just like gravity, and repulsive. Which gravity is not. Gravity is always an attractive force. Whenever you have masses, they are always attracted to each other. The force between them is always pulling them together. Electrostatic force can be both attractive and repulsive, which makes it fundamentally different from gravity. Okay? It can push things apart or pull them together. Okay? And so what we see is that opposite charges attract. Okay, so here if we have a plus charge and a negative charge, they will be attracted to each other. And like charges repel. Okay, so if we have two positive charges, they're going to push each other away. Okay? Or if we have two negative charges, they're going to push each other away. Okay? This is the reason that we've come up with these names, defining them as positive and negative, because we know that if you multiply negative by negative, you get a positive again, right? So this tells you the signs of them. So if they're opposite signs, they're always attractive. If they're the same signs, they're always repulsive. Okay? So let's show that that is true here. So okay, so I'm going to charge back up the styrofoam balls. So I've got this one, which is once again the saran wrap, the plastic wrap, will tend to take electrons off of this ball, so it'll make it positive. I'm going to do that on this side too. And then the other side, I'm going to rub with the fur. Okay, and let's see if I did a good job on those or not. Okay, so these are the two that I rubbed with the plastic wrap. I need to balance this just a little bit. Okay, these are the two I rubbed with the plastic wrap. You can already see that these should have the same charge because I rubbed them with the same material. And you can see they're definitely repelling each other, right? So this does not want to balance. Okay, so definitely a repulsive force between the two like charges, right? So this one I charged with the fur, and you can see that this is hopefully attracting. I might have to charge this back up again. I think the saran wrap works a lot better, so I'm getting much more charge on this side. But there we go. You can see me. You can at least see me pulling it around here. Pull it back. Come on. Friction. Friction always wants to come in. Okay, so you can see that at least we demonstrated here that these can be both repulsive or attractive. Okay, so let me go back and charge this one up again. So this one should have the same charge as that one, which we were calling negative. So let's see if these now repel each other. I think I might have lost the charge in that one. Let's see if these ones are attracting. Yeah, those ones are definitely attracting. You know you guys want to do this when you go home. Okay, plastic wrap and fur. Okay, and let me, or socks. I think walking across carpets will give you the same effect. Okay, let me charge that one back up just a little bit, at least just to show that if we have the same charge of the opposite, that it's going to be repulsive as well. Yeah, I think the fur doesn't quite do as much charge as the plastic wrap does. I'm resisting the temptation just to hit this. That would be cheating. There we go, a little bit. So just a much smaller charge, so it just took longer for it to pick up. I'm not blowing on it, by the way. Okay, so opposite charges attract, like charges always repel, and there's two types of charges, positive and negative. Okay? And for most objects in the world, if they are negatively charged, it's because they have gained electrons, not lost protons. If they're positively charged, it's because they have lost electrons, right? And they retain the protons to keep the positive charge. Okay, so force. This is a force. It's attractive or repulsive. So if we have a force acting on these particles, the electrons or the positrons, sorry, the protons, then the force is going to produce accelerations. Okay. Remember, once we have a force, we can go back to Newton's laws, right? Force is just equal to mass times acceleration. So if they have the same force on them, remember the electron is 1/2000th the mass of the proton. So for the same force, how fast they are accelerated depends on their mass, and so that means the electrons are going to be accelerated much faster, okay, or much more rapidly than the protons. And so that's why when we have currents flowing, electrical charges moving, it's almost always electrons that are moving, okay, just because they move so fast with respect to protons. Okay, so let's look at the strength of the electrical force compared to gravity. So we now have two fundamental forces. We can pit them off against each other in a death match and see which one wins. Okay. Let's look at the strength of these two forces relative to each other. So let's start with two electrons. Okay. So here we have our two electrons. I put a negative sign there. We know they have a negative charge, -1. Okay. There are two forces we know about acting on those electrons that are sitting there. Okay. First off, they have masses. The fact that they have mass means that there's going to be gravitational force that is attracting the two of them together. But now they also have charges, and we know that the electrostatic force is going to be repelling them from each other. And if we look at the ratio of those forces, so the electrical force over the gravitational force, okay, the ratio of that is a surprisingly large number. It's 4 times 10 to the 42nd. Okay. The electrical force is 42 orders of magnitude stronger than the gravitational force between those two particles. Okay. So that means we can pretty much ignore gravity whenever we get charges together. Okay. And the motion of these are going to be completely dominated by the electrical forces between them. Okay. So you can think of this as gravity is either extremely weak force or electrostatic forces are extremely strong, or both. Okay, so electrical force is much, much larger than gravitational force. So given that, you might ask a very relevant and important question of why so far in the class we've been studying mostly gravitational force, and it seems to dominate the world around us. Okay? We're not, if we were dominated by the electrostatic force, then we wouldn't just have gravity pulling us down to the surface of the Earth. We might actually be occasionally flying up to the ceilings because it's repulsive or attractive, right? And it's a much stronger force, so why would we care about gravity at all? And the reason that is because because the electrostatic force can be positive, it can be attractive or repulsive. And it's got 2 charges. It's got positive and negative, and we know that they're balanced on the whole. And so, so if you have an object that has no net charge, then it's not going to be subject to electrostatic forces. And we also know something else, which is maybe a little counterintuitive until you think about it, which is the fact that the electrical force is so much stronger than the gravitational force, and the electrons themselves are they're so less massive, they're so light, which means that when we do get electrical charges in the world around us, the electrons will move very quickly to try to cancel that out. Okay, so on the average, in the world around us, everything is pretty much neutral. Occasionally we get a shock when we're walking across carpets, or you touch a car door, which means that we have created some electrical charge. Okay? But on average, those are pretty much all canceled out by the fact that this force is so strong and the electrons move so quickly that if there is a net charge, it will tend to cancel out, okay, and disappear. Okay, so let's do this calculation for protons, which is a little bit of a side note, but I think it's interesting. So for 2 protons, remember protons have the same charge as electron, just opposite sign, but they're 2,000 times more massive, which means that gravity will be much stronger between them. So if we have 2 protons, so they're going to be attracted by gravity once again. They're going to be repelled by the electrostatic force. Okay, and we can look at the average of that, the ratio of that, the electrical to the gravitational force. Okay, and this one isn't quite so large, but it's still huge. It's 10 to the 36. Okay, so that means that the electrical force is still many, many orders of magnitude larger than the gravitational force. Okay. But now remember our picture of a nucleus. where we have protons that are very tightly bound together. They're bound with neutrons. And you might ask, why are those protons bound together? Why aren't they repelling each other, okay, and basically blowing the nucleus apart, right? Like we know, the electrical force is very, very strong. It's much stronger than the gravitational force between them, okay? And so this is only true because there is yet another fundamental force, which we call the strong force, which is even stronger than the electrical force, which is holding the protons and neutrons together. Okay? So we're not going to talk more about that right now, but I just wanted to bring that up. And we will probably talk about that more later when we talk more about quantum mechanics and nuclear structure. Certainly when we get to nuclear physics in the last week of the semester, we'll be talking about this. Okay, so those protons, there must be another force even stronger. Now, you might also ask, why aren't all the protons, if there's another force that's even stronger, why aren't all the protons in the universe getting sucked together into one giant nucleus, okay, if there's such a strong force? Well, the reason is that the strong force also is unlike the other two, that it only acts for a very short distance. Okay? So most protons do not feel a strong force the other protons in the universe. They only feel them when they're already at nuclear distances. And we've already seen that most of the atoms, right, most of the material is made up of huge empty space. Okay? That's good, because that means these protons don't get close enough together for the strong force to take hold and attract them. Okay, so I said a statement which is partly true, which is that in our everyday world around us, we're much more dominated by gravitational forces than electrostatic forces. Okay? That is partly true, except for one very fundamental thing which we take for granted, which is we've already been talking about electrostatic forces quite a lot in this class. We just didn't call them that. Okay? And that's when we've been talking about normal forces. Okay? So normal force is, remember, the force that holds things up. So the normal force of the table on that piece of chalk is countering its weight, so countering gravity and holding it there. Okay? Now at the microscopic level, remember that chalk is just made up of atoms. This table is made up of atoms, and we know atoms are empty space. The first order atoms are completely empty space with just very tiny nucleus and very tiny electron. Right? So why isn't that chalk pulling a kitty pryde, I guess, and falling through that table, even because they're all empty space? And that's because of the electrons. So the electrons in the chalk and the electrons in the table are very strongly repulsive of each other, just like all the electrons in the atoms in the table are very strongly repulsive of each other. And so they are keeping the atoms separated from each other. So the normal force itself is an electrostatic force, and it's one on the microscopic level. It's individual electrons repelling other individual electrons. Even though on average this is not charged and the table is not charged, okay, they are not, that chalk's not being flown up by the table, pushed away by the table, or attracted to the table. But when you get the two atoms together at the microscopic level, the electrons get really close and they repel each other. Okay, so there is a net force there that's keeping the atoms separated from each other. So electrostatic forces actually do play a very large role in the world around us, even when the objects are neutral, like this. Okay, so let me define two types of materials. which are first off conductors and then insulators. Okay, so conductors. We define conductors, or electrical conductors, are materials through which electrical charge can flow, can easily flow. So material through which charge, and by charge we usually mean electrons, can easily flow. Okay. And you guys are probably already familiar with the most common conductors, which are metals. Okay, so that's why we make wire, like the wiring in our wall, out of metal, because charge can flow very easily through metals. Water is a pretty good conductor, and as a consequence, since we're made up mostly of water, humans are a pretty good conductor of electricity too. So not as good as metals, but certainly we're not insulators. So insulators are the opposite. They're materials where charge does not flow very easily. Materials that do not readily let charge flow. Okay, and you probably know most of these from just common everyday experience. So examples are plastics, glass, and rubber. So that's a good reason why our soles of our shoes are made out of rubber, so we don't get shocked quite so much. So conductors are insulators. Okay, so we can create net charges on both types of materials, so on conductors and insulators. For example, these styrofoam balls are pretty good insulators, okay, but we can charge them up. One difference between them is that charge will flow much easier from a conductor, so it's a lot easier to discharge a metal object than, for example, these styrofoam balls, which tend to stay charged up once we charge them. Okay, so we have introduced a new force, the electrostatic force. So it's probably not surprising that we're going to introduce a new type of energy to go with that. Just like when we introduce gravitational force, we have gravitational potential energy. When we introduced the elastic forces, we had elastic potential energy. Okay. Likewise, we've introduced electrostatic force, which means that there is energy associated with that. So that's going to be the electrostatic potential energy. Okay, so it's really easy to figure out where this would come from. Let's take two objects. Say these are metal plates, or I'm going to draw them like this, but these could just as easily be our styrofoam balls. Okay. And remember, we can't create a net charge, but we can transfer charge from one to the other and create areas of positive charge and areas of negative charge. Right? So if we separate the charge on these two, so we have a positive on one side and a negative on the other side, okay, those are going to be charged and they're attracting each other. Right? There's an electrostatic force between them. Okay, so if we pull those apart, okay, so we're going to grab those plates and just physically pull them apart. Okay, there is an attractive force between them. The electrical force, electrostatic force, okay, which wants to pull them back together, which means that in order to pull them apart, in order to separate those charges, to physically separate charges, we had to do work. we had to do work on that system to separate those two charges, which means that there is energy in that system. Right? And that energy comes from the fact that these charges want to basically jump between the plates. Okay? So there are a number of ways we can get that energy back out, okay, which we'll be talking about this lecture and next lecture. But there is definitely potential energy stored in this configuration. Okay, so let me do some demos so we can see that there's energy stored in this. Okay, so first off, this is a dramatic but not particularly useful demonstration of this. Okay. I've got two metal balls here. I don't want to touch them. This is actually kind of dangerous. So there's two metal balls. I'm going to be charging them up, so I have a net positive charge on one and a net negative charge on the other. Okay, so this is charging up to 2,000 volts, which we'll talk about in just a minute, what 2,000 volts is. Okay. So I'm going to turn the microphone off. Okay, this is slowly charging. We're almost up to 1,000 volts right now. Charging. Energy. I'm doing work on this. Okay, so this is a problem with electrostatic demos. It's hard to show electrons moving. Okay. So there we go. That should be pretty good. Okay, so I'm not sure what has the microphone on here. So there's definitely a lot of energy stored in that system, right? So remember, electrostatic force is very strong force. So we can create a lot of energy in there, okay, with the electrical forces. By the way, I know some of you guys like to come down here after class and play with stuff. Please do not touch this one, okay? This is the dangerous demo here today. So okay, so let me do another demo of this. This is called a Van de Graaff generator. And you can basically think of this as there's a little conveyor belt in here. And this conveyor belt is basically like somebody walking across the carpet continuously. It's just creating a net charge, and it's going to be charging up this sphere up here. So this is connected to the spring, which is a copper wire, down to this plate. So it should be producing a net positive charge on the top plate and a net negative charge on the bottom plate. Okay. These are metals, so they're conductors. So that means charge flows very easily to them, but it also flows very easily out of them. So I'm hoping this is going to work. We were having some problems with this before class. Come on. There we go. You can see that it's pulled that plate down and touched. Okay, and then once it actually touches it, it will transfer the charge between the two of them and let them go. So as it's charging up, it produces an attractive force, okay, pulling the plates together. Okay, and then once the plates actually touch each other, that current can flow, the electrons can flow from one to the other, and it will separate back. So there we go. Now it's warming up. Okay, but you can definitely see here that the electrostatic charges are doing work, right? They are moving this plate up and down on this spring, okay, a little bit randomly. Okay, so this is not the usual way we recover energy from electrostatic forces. The usual way is we've got our charged plates or our charged regions or batteries or our wall socket, okay? And we recover energy by letting charge flow between them. Okay, so we usually recover energy by letting charge flow. Okay, so the idea is that we have our positive charge region, our negative charge region. Okay, we know that they are attracting each other. Okay, we can either let the whole plates come together, or we can just let individual charges. Remember, the charges that move are electrons flow between them. So the way we usually get this energy out is by connecting with a wire or some sort of conductor and letting charge flow between them. So this is the same thing as dropping a ball in a gravitational field. You lift it up, we get the energy back from letting the ball drop. Same thing here, we've taken these charges, we've moved them apart so they have a potential energy, and we get that back by letting them go. But that's usually electrons flowing up to the positive plate. Okay? So when they're flowing, they're recovering this energy that's stored in the potential field. And then depending on what you do with this wire, right, you can get that energy out. So, for example, one, of course, very common example is to put a light bulb, for example, in that wire. So we've got just charges running through it, okay, recovering the energy. This is actually just plugged into the wall right now. What I want to do here is actually, this is a set of, basically they're called capacitors, which are really just plates like this, okay, lots of them, which store potential energy by letting us separate the charges between them. Okay, and if I charge them up, so I'm charging up these plates in here right now. Okay. I'm going to let them discharge by flowing through this wire with a little light bulb there. So there's our light bulb right in the middle of that wire. Okay, so they are all charged up. This is going to be the most anti-dramatic demo ever. When it discharges, boop, we've created a little bit of light there from letting the charge flow. So we're charging those up, okay, and letting it out. Okay, so you can imagine that if we really wanted to store a lot of charge, we'd probably have a much, much larger set of capacitors and plates here to let that out. Okay? But it's definitely a convenient way of storing energy. Okay? It's a lot easier than creating, batteries of giant lead balls that we let fall back to Earth, right? So much more convenient way of storing battery for your, storing energy, for example, for your iPhone. Okay, so that is charge flowing through a conductor. Now we can have charge that flows not through a conductor, but through let's see, oops. There we go. Okay, so I disconnected, let me turn this off. Things are going crazy here. Okay, so I'm going to move this over just a little bit. There we go. Okay, so I've disconnected this from these plates. So now all I'm going to do is charge that up. Don't touch that. Thank you. I'm wearing rubber shoes. Good job today. Okay, so Normally, charge flows through a conductor, but it doesn't have to. So we do have to be a little bit careful with electricity. Okay, I'm just charging up this this rod, and I can't point at it. That's bad for me to point at it. So I'm using my fist. Okay, I'm charging it up, and it's getting enough charge that it's it doesn't care that there's not a wire there. It's going to send those electrons sparking across that gap to the other one. Okay? Air is a conductor, but it's not a very good conductor. It's a very poor conductor. But if you get enough electrical charge, it's going to flow. Okay? So this whole thing is charging up. Oh. Let's see. Like I said, the electrostatic force is very strong. We can do this with people, but let me do this without, at least to start to. Imagine that as somebody's cool hair. Okay, when we're charging this up, remember, like charges repel. So we're charging up the all these pieces of paper, and they don't like to be next to each other. So they're trying to repel each other as much as they can, okay? Producing this cool pattern. I don't know what's going on with this guy. Maybe I do have those superpowers that I thought I had when I was a kid. So you're probably doubting whether I'm right. Okay, so let me discharge this. Okay, let me do one more demo of this, which is really made just to annoy the people in back. Okay. Hey, it's working great now. I can't even stand next to it without getting shocked, so thank you. Okay, so I got a little plate here, and I'm just putting a bunch of puffed rice in it, so it's like breakfast cereal. Puffed rice is not a very good conductor, but it definitely can get charged. And let's see what happens here. Yeah, sorry about that in back. Okay, you can see, oh, that's working really well now. I'm not going to let anybody touch this because we were having problems with it earlier. It's creating a lot of charge on this. Wouldn't hurt anybody, but it probably would not feel particularly good. Okay, so like charges repel, right? Same charges, opposite charges attract. That is the electrostatic force. Okay? So let's see. I think I'm just getting close to it. My hair is probably already standing a little bit on end. I can feel it. Okay, one more thing I want to say today, and actually we're going to go a couple minutes early. Let me discharge this. Okay, so electrostatic potential energy. Okay, so we've talked about energy a lot, and we're going to introduce a new unit here, which is called voltage, or volts. It's something that we are all very commonly use. And let's just relate this to the electrostatic potential energy. So voltage, we know batteries have a voltage, the power on your wall has a voltage, this has a high voltage. Voltage is just a measure of the amount of energy, potential energy so it's the potential energy, okay, a charge would gain back by flowing between these two plates. Okay, so it is the amount of electrostatic potential energy per charge. Okay, so it's just an energy, but it's an energy per charge. It's not the total amount of energy. So the voltage is equal to the potential energy per charge. Okay. So that means that a voltage by itself is actually not particularly dangerous. For example, this charged up to 2,000 volts. Okay? The voltage itself isn't particularly dangerous. Okay? What's dangerous is how much charge you let flow, okay? Because the more charge flows, the more energy you get out of it. Okay? So if this is a high voltage, but there's not any current flowing between there, there's no energy that's being transferred. Okay? If I just let one single electron go between there, that's not going to produce that much energy. Okay? But if you let large current flow over this voltage, you're going to start getting back a lot more energy. So the voltage is just the potential energy per charge. Okay? So when we're looking at the energetics next time, voltages and currents, we have to remember that to get the total amount of energy, you have to multiply the voltage by the total charge that's being transferred. So, okay. So we'll pick up there next time to talk about currents and circuits.